Hi everyone, welcome to SMARS Fan Live. I'm your host Kevin McAleer, and today we'll be looking at Python and coding that with VS Code and using a Raspberry Pi Zero with the header and Wi-Fi. So for people who are just finding this on YouTube, just to let you know what SMARS is, it's an amazing low-cost open-source 3D printable robot that's very easy to print yourself and assemble. Very little electronics or programming skills required, and this is what this series is about, is to sort of upskill people and get them excited about robotics. So what we'll cover today then is we're going to write a program, Hello World program, as is tradition with learning new languages. We're going to get some input from the keyboard. We are going to write a function. We're going to look at some libraries, and as a bonus we're going to look at SMARS Fan Lab, which is a piece of code I've written and a library I've written, and that's working on our quad robot. So if I just quickly go over to our SMARS cam there, you can see I've got the quad, I've got a Raspberry Pi Zero just there. You can see it's got a little shiny chip there, means it's the Wi-Fi enabled one, and this thing is just sat there waiting for us to load some code in it. So let's get to the preamble. So what I will do, I'll just move over to Keynote. There we go. So we're going to look at Python first of all. So just to introduce what this is, what is Python? It's a programming language used by scientists, makers, businesses, web developers. It's one of the fastest growing languages. I think it's second only to Java, which is kind of on the descendancy, really. That's on the way out. The difference between this and say Arduino is that when you compile an Arduino program, you end up with compile code. It's a machine code for that specific chip, for the 80 mega chip. Python is a bit like Java in that it doesn't actually get compiled, it's interpreted line by line. So when you run the Python script, the interpreter will go over each line one line at a time and then compile that into what it calls bytecode. So this is like a virtual machine, and this is why it's quite portable. It can be used on all kinds of chips, and we'll have a look at some of those in just a minute. One of the things I like about Python, it's very easy to read and write, much easier I find than say the Arduino C language, and we can see an example of that in a minute. And also because it's quite a modern language, it's it's not that old compared to something like C, which dates back to I guess the 70s and 80s. This is a sort of language of the 2000s. So because of that, it's much more aware of things like World Wide Web, data connectivity, and it can connect to other systems. So there's loads of libraries that make that very easy. And there's a whole wide base of these libraries at something called PyPy, which we can have a look at as well. So why is it called Python? That's one of the questions I was thinking. It's got nothing to do with snakes, funnily enough. It's to do with Monty Python, the British TV show from the 70s. So the inventor of Python, Guido van Rossum, he was reading through some scripts of Monty Python's Flying Circus, and he was looking to name this language, and he wanted something short, unique, and slightly mysterious, so he decided upon Python. So it kind of stuck. So where'd you get it from? If you go to python.org, you can see a bit of a web clip there. You can see that this is where you can download it. You can click the great big download button there, and you can download it to your specific type of machine. So if you've got Windows, Mac, Linux, whatever type of machine, you can get a flavour of Python from there. And they've also got things like links to the PyPy, which is the library, and also documentation and so on. So it's a really good resource. They really keep it fresh, and Python is continually being improved and developed. So one of the questions is, why should we use this? Why should we switch from our Arduino, which we're quite comfortable with, to using something like Python? Well, as I said, it's easier, cleaner, and faster to write. So compare this code on the left here, which is kind of a Arduino or C. We've got to use things like void. We have to use the camel case. We have to have these squiggly brackets, and every line has to end with this sort of semicolon thing. And we have to use some quite obscure C things as well. And then when we want to run that code that we just created there, we then have to do another thing, which is the void main, or the loop in Arduino, and now we have to run it again using the little squiggly brackets and the semicolon. Compare that to the same piece of code for Python. It's much cleaner, much easier to write. There's a speech marks missing just there, I've noticed. So much easier to write and to read. So why should we use this? Why should we choose to look at this over something else? So I'm just going to bring up me in the corner there. So it's used by Adafruit. They've really invested in this. I've got some chips here that they've been developing. So you might have heard of the Circuit Python. So I've got a little chip there, which is one of their earlier versions of this. They called it Circuit Playground then, but it's essentially a little chip which can run Python. And it's got all these connectors around the edge, so you can connect crocodile clips to that. You've got sensors on board, you've got little buttons and all kinds of clever things on there. So that's a Circuit Python. Adafruit also produced this thing called a Cricket. So this is like a motor shield, but for a microbit. I've got a microbit robot here, just to hand. This is a little Kittronics kit. Looks quite similar to that Vector, but probably a little bit cheaper, and it's got things like servos in there. You build it yourself, quite easy to sort of put together. But that's actually a microbit that's just sat in there. It's got a battery behind it, and I could pull that out and put it into here, plug in some motors into these headers there, and control it. The only thing is it's a little bit wide. It's a bit the wrong shape for my liking. So microbits can use Python, Circuit Python, and something called MicroPython, which can run on these chips. This is the Node MCU chip. So I've made quite a few little projects like this little box here that can make a flag go up, and inside there's just a little servo connected to that. And on this side, if I just pull the end cap off there, there's a Node MCU, one of these chips, just sat in there. So these things are great because, again, very cheap. They have Wi-Fi. That little chip there is the Wi-Fi module, and they're 32-bit, so they can run quite a lot of code that you wouldn't be able to get away with on an Arduino. So really, that's what this is about. We use Python because it's a language that's it's a bigger language than the Arduino would allow. Arduino is for 8-bit chips, and it's designed around that and the low memory limitations of that. Whereas Python is bigger, and it's designed around 32 and 64-bit chips. So MicroPython can be used on these chips because of that. And things like Wi-Fi, TCP/IP, which is what you use to connect over the internet, web APIs, application programming interfaces, all these things very easy to use with Python. Whereas with the Arduino, it's quite difficult to use these things because it's only 8-bit, and it doesn't have that range of memory to be able to store these things in and use. So one of the reasons that we want to use it is it's kind of a more grown-up version and more modern. So who uses it? You can see there's a lot of different companies that use it. Netflix, Amazon, Google use it. You might remember the black hole that was discovered, and NASA used Python to do a lot of the image processing of that. So it's quite heavy lifting. It's very good at data manipulation. There's a whole load of frameworks that enable you to do things like looking through large data sets and pulling out the insight that you're looking for, the data mining. So that's called Panda. So yes, lots of companies use it, and because of that, it's being invested in. So how do we get started? We want to use this now. So what we're going to do is we're going to get a hold of Python 3. So you might see, or you might have on your machine already, Python, but it might well be Python 2.7. That's very common, particularly on Macintoshes. They come with that installed. We don't want that version. That's the old version. That went end of life in January this year. What we want to have is Python 3 upwards. So 3.5, 3.8. I think 3.9 is just in release at the moment. So we want a high version of Python, version 3 above. We want to set up a virtual environment. So if you remember when you code on an Arduino, one of the issues that you might come up against if you use one or more machines, if you're using 2 computers to do your development on, is keeping your libraries in sync. So you might install some library like the Adafruit Motor Shield library, and you might forget which one you used. All that kind of library management is something that they've taken care of in Python, and that's what PyPy or pip is for. So pip installs, we'll come to that in a minute. It's to do with library management. So what we want to do is set up a virtual environment. It's very, very easy to do, very quick. And we also want to set a goal of what we want to achieve. So what is it we're trying to achieve with this, and that'll help focus our mind. So what we want to do, first of all, is write a hello world program, and then we want to write a program that will grab some input from the keyboard and spit it back out. And then we can kind of take it from there really and see what we can do. So we can also write some tests as well. It's always good idea to write tests as you go along with your code, and also share your code at the end. So I'll show you how we can do all these things very simply. So there's different development environments that we can use. So what we're going to look at today is running the code on the Raspberry Pi, but we're actually going to create it on the Macintosh that I'm using in front of me. I've got an iMac in front of me. So when you get Python, you have something called idle, which is this integrated development and learning environment. It's a bit naff, it's basic, it does work, but it doesn't have all the nice features that some of the more advanced tools use, such as Atom and VS Code. Atom and VS Code are both free, both extensible. You can get plugins and things for them, so they're very worth looking at as well. If you don't mind paying a bit of extra money, you can look at PyCharm, which is a dedicated environment for developing Python. And then with the Raspberry Pi, you get two environments for developing. You get Mu and Thonny, and both of them have got the pros and cons. Thonny's a little bit more advanced than Mu. Both of them enable you to connect to a chip and upload and download code, a little bit like the Arduino. So for this, we're going to be using VS Code, but I was quite a happy fan of Atom for quite a long time, but for me, VS Code is just slightly better as a piece of software. So one of the things we need to sort of familiarise ourselves with is reserved words. So when we're putting together our programs, these are words that we can't use as names of things. These are special words that have been reserved in the language. And it's things that you would expect really, so things like if, while, not, or, true or false. True and false are actually capital T and lowercase rue, capital F, lowercase alse. We can get to that and do some testing around that. And there's things like class, break, assert, and an as. All these different things, and def is what we use to define functions. So we can get into that when we start cutting some code in a minute, but there's not many to actually learn there. That's quite a small set of things not to use. And one of the things that Python has that enables us to very quickly get up to speed and sort of hack around and try things out is what they call the REPL. And when we start using the little chips like this Node MCU to load MicroPython, that's one of the main ways that we will interface with the chip, is through this thing called a REPL, and it's an interactive command line. So we can issue commands to it. It will will execute the code that we give it. It will then print back the results, and we can get it to run code. So that's what REPL stands for: read, evaluate, print, and loop. One of the things that Python has above the Arduino is things like lists. So on an Arduino, when you create an array and you've got several values of a specific type that you want to store in a list, essentially, you can do that. But with Python, it's really good for sets and lists and dictionaries. So we can mix what's in the array, and you can't do that in C on the Arduino. So if you look at this example here we've got on screen, we've got front left, right, front right, back left, and back right. These are representing the legs, for example, on our SMARS quad. We've got some angles there that we might want to store, and then what we can then do is we can combine those two lists together. So if we say this is a piece of Python code for item in mixed, and item is just a variable name, mixed is the name of our list there, we can say, for each of them, then execute this piece of code over and over until it's exhausted it, until it's iterated through all the items in there. So it'll go to the first one, legs, it'll print out that legs is an array of these things, and then it'll get to the next one, which is angles, and then it will print out the array there as well. If we wanted to, we could nest another for statement within that and then go through each of these. But the code itself, very clean, very easy to understand. So lists are a real bonus and help us do some interesting things. And because we can do this mixing of things, there's this idea of dictionaries, or tuples as they're often called, and it's key value pairs. So you often have a key, such as in this example here, we've got a dictionary that's called animals, and we're going to say that there's an element in the dictionary that's called bird, and when we look at bird, it will link together the value sparrow with that. So bird and sparrow are sort of linked together there. So that's the key. Bird is the key and sparrow is the value. And we've got cat there, and we've got British short hair as the value. So what that means we can do is we can put things in a list, in a dictionary, sorry, and we can very quickly find things in that dictionary that we're interested in. So it's very useful for storing things like configuration details, and just generally very useful. Very, very powerful tool, that. And then for control statements, we've very similar to the Arduino. We've got if, else, while, for, but we have this range thing. So if we wanted to loop through on an Arduino, we would have to use some kind of counter variable to say, loop while count is less than 1. What we can do in Python is use a range, and we can say the range is 1.12, and it'll go from 1 to 12, or 24.2, and it'll count down. So we can define a range, and it will guess what the values in between that range are. So very powerful new piece of code for us there. And these virtual environments, so again, as I said, this is to do with, there you go, pip stands for pip installs packages, and pip is what we use to manage our libraries. And we'll see in a minute why this is quite useful. Helps with things like versioning. It helps us capture which libraries we've actually used, which we can't do on the Arduino. So this is definitely a plus. So that's the preamble. Let's get over to our code. And just before we do that, what I'd like to do, just to get a bit more of interactivity with people on these videos, I'm going to do a comment of the not comment of the week, but comment of the last video, comment winner. So on the line following video that we did on Friday, we had a comment from Carpe Diem, and he's very kindly said, "You are the man, I really like what you're doing, keep on." So he's the comment winner of the last video. So if you want to be the comment winner for this video, please comment on the YouTube video, and you can be the next winner. Great, so let's get over to our environment. So first of all, I'm on my iMac here. You can see it says iMac, oops. And what I'm going to do is I'm just going to go into my Documents and Python folder, and I'm going to go into Lesson 8, which is just there. So inside Lesson 8, if I just clear the screen, we can see there's a README. If I just look into that README file, we can just say, it just says hash hello, and that's it. So if we open up VS Code, so I've got VS Code here, we can see we're in the same folder, we've got our hello file there, and we've not got anything else. So what we're going to do first of all is we're going to create a new Git repository, and this will help us maintain our code and share it over to the Raspberry Pi. So the first thing I'm going to do is going to go git init, and git init creates a new environment for us, a new repository, and the next thing we need to do is add to that the files that we're interested in. We can either do add readme and type that in, or we can just do add dot, which will just add everything in. So if I now do git status, we can see we've not committed anything yet, but we have added a new file called readme. If I now just do a git commit and do m for a message, and I'll just say initial commit. So that's now been committed. Now that's still just stored locally on my machine. That's not anywhere on the World Wide Web yet. So what I want to do, just to make sure that this works with VS Code, is I'm going to load up GitHub Desktop. I'm going to add in, just need to find that repository that we've just created, and we're going to add that in and then publish it. So I just need to go to Lesson 8, open that up, add that repository to my list. It can see that it's not been published, so I just need to publish it. I'm going to call it Lesson 8 Python Intro. I'm going to make sure everybody can see what that is, and this is Lesson 8 Python Introduction. Well, let's publish that. So just take it a moment to do that. So I'm just having a question on the chat. there from, how do you pronounce your name? Is it Svenborn? Svenborn? I'm not very good at guessing that's a Swedish name. But yeah, ask away. Happy to answer that on the chat. Okay, and that can help fill any gaps while things are happening. Right, so what's happening now is that's now been published up to GitHub. We can check that out on GitHub if I go over to GitHub and we look for lesson 8. There it is, which has just been created 42 seconds ago, and we've just got one file in there, and we can see the initial commit. That's the message that I created. Right, so let's now go to VS Code. Now VS Code is aware of Git. It understands how to synchronize things. In fact, that's what this little USB type icon here is. It's the source code control. That represents the branching of code. And what we mean by branching is when we're working on a piece of code, you can consider that to be the sort of branch of the trunk of a tree, and we might decide that we want to try a little experiment, so we can branch off that tree a separate piece of code, and when we're happy with it, we can merge the code back into the original source master branch of the code, and that enables us to work on many different things at the same time, but then bring them together into one piece of one repository, so and keep everything in sync. And Git's really clever at working out the differences, what it needs to do in the background, and what we will do just to illustrate that is where we've got the master branch here, we can create a new branch, and we will call this new branch try KMC, which is my initials, and we'll call it hello. My cat's meowing loudly there. Right, so what's happened now, if you look down at the bottom of the screen, if I just move this up a bit, we can see there, this is the branch name. So we were on master, and we are now on try KMC hello. And these funny little numbers and letters after the name of the branch, they're the reference that Git uses in the background. It will create these hashes, and that's how it compares everything. It's very dependent on hashes. And this little cloud thing with the up thing means that this is a local thing. We need to publish that change if we want to push it up to the cloud. It will push it up to GitHub. And it's now in sync. So now we can create some new code. Right, let's actually get to creating some code. So what I'm going to do first of all, I'm just going to create one that's called hello world. I'll do hello_world. That's the snake case, if you remember from the previous video. Snake case because it's got the little line, it looks like a snake. And we use the .py at the end to represent that this is a Python file. So what we need to do then is we just want to print and then hello world. And let's just save that. So I'm just going to do Command and S. And what we can do, we can also just run it straight from here. And you can see there, it's opened up a little terminal at the bottom of my screen. It's executed the command Python and then the name of the file, which is hello world.py. So we can, if I just clear that screen there, if I type in Python 3, because we haven't created our virtual environment yet, if I just run Python, it will probably still work, but it will probably run it under Python 2. So if I do version there, we can see it thinks we're on version 2.7. We don't want 2.7, we want version 3 or above. So this is a good opportunity for us to create our virtual environment. Okay, so let's create our first virtual environment. So what we need to do, we can do this a number of ways. Let's go back to our big command line there so we can see what we're typing. Let's clear the screen. And what we're going to do is we're going to type Python 3 -m venv. And what this stands for is virtual environment. And I'm going to create a virtual environment that's called venv. Let's just do that and see what it does. It'll take a couple of seconds. It's going to create a folder called venv, and it's going to put in there a couple of files. And that's kind of like a copy of Python just for this one folder. So if I do ls to look what's going on, we can see this new folder that's called venv. Let's just list it so we can see there that it is a folder. And if we have a look inside that folder, let's have a look what we've got. We've got some bits and bobs. We've got a binaries folder, we've got a libraries folder, we've got an includes folder, and we've got this pyvnv.config file. So what we need to do to activate this, we want to actually use that library. We want to activate it. So we type the command source, and this is the same if you're using Windows, you're using Mac, you're using Linux, it all works in the same way. So we type source, we type venv, we type bin for the binaries folder, and we type the command activate. And you can now see that we've got this little brackets venv, and we are now using that new version of Python. So if I do python -- version, we can now see that we're on 3.8.2, which is the latest version that we've got installed on this Macintosh anyway. I think there's maybe a very slightly new version, 3.85, something like that. And if we want to deactivate that now, we just type deactivate. And if we now just do Python version, you can see that it's now using the 2.7.16, which is not what we want. So let's go back to our source so that we're now in our version that's 3.8.2. And let's execute that file. So if I now type Python, it will actually run the version 3. And if we do that without any parameters after it, you can see there it says Python 3.8.2, and it's got some information about the build. And we're now in this REPL, we're now in this read, execute, print loop cycle. So if we type in a equals 1, and then we type a, it prints out 1, the value that's in there. So we can use this to look at things, we can use this to examine our code or just run little tests and things. However, what we want to do is we want to give the parameter, which is the name of the file we just created, hello-world.py, and there you go. It's just going to write out to the screen hello world. So very simple program. It's literally just a single line of code. Couldn't be any simpler there. Now Visual Studio has actually noticed there, we've noticed a new virtual environment has been created. Do you want to select this for this workspace? Yes, we do. We want to use that that we've just created. It's also noticed that this linter is not installed, pylint. I'll just see if it can install that. It's not a problem. It can't. There we go. So it's just going to do some things in the background. It's going to install pylint, and that will help us with our code. Okay, and it's also warning us that pip, which is at the package installer, is not quite the latest version. So it's telling us there we should run this command, pip install upgrade pip. I'm just going to copy that and paste that and run it. And what that will do is that virtual environment we just created will then have the absolute latest version of pip. And it means any new bug fixes or any new features that they've included, we'll be able to make use of that. Okay, so hopefully you're still following along with me there. So what we're going to do now is we're going to get some input from the keyboard. So this is all very well and good. It's not a very useful program to us. So let's create a new file, and we'll call this one name.py. So on this one, what we're going to do is we're going to write input, and then we're going to say what we want it to say at the input. So please type your name, and the beginning of that line I'm going to say name equals input, and then what I'm then going to do is say print name. So let's try print comma name. So hello and then name. Let's try it without the space actually. I think Python's quite clever like that. So if I run that, so you can see the screen there, it's saying please type your name. So I'm going to type in Kevin, into the terminal. I'm going to type in Kevin. And then it says hello Kevin. Now notice it's even put the space in for us. That's how clever it is. It knows that that's a string, but it knows normally you separate them. So it's quite clever. It's even put that space in for us. So this is how we can get input from the keyboard. Now notice that we didn't even have to define that name was a string. That's quite a common thing with Python. You don't need to define the types of things. One of the differences between Python and Arduino is that it's dynamically typed, it's not statically typed, and that means that we don't need to define our variables before we use them. It is case sensitive, so if we did uppercase N for name and did lowercase here, it wouldn't work. It is case sensitive. However, we don't have to define what they are. In fact, everything in Python is an object. So if we go back to our command line there, and we just go back into the interpreter, the REPL environment for a second, and we say name equals, and then do that, Kevin. We say name, it's going to print out what's in that value, but we can actually is it type dir name. So name is actually an object, and it's a string object, and because it's a string object, it's got all the things that a string object would have. So it's got all these different things like title, uppercase, lowercase, stripping out spaces in there. So if we do name.upper, it's now printed out the name. If I just move this up so you can actually see what's going on, it's printed out the name Kevin, but in uppercase. If we do we set name to equal Kevin space McAleer, like that, and then we do name.strip. Is that not the one? Is it trim? It's going to look through what we've got there. I thought strip got rid of all the spaces in there. Is it trim? Nah, I can't remember. Okay, so I'm getting away from off topic there, so let's just come out of that. And let's get back to our code. So that's great, we've got a bit of interactivity there, we can get stuff from the terminal. But what we want to do, our goal is to be able to control robots. That's what we're learning this for. So to be able to do that, we need to be able to create functions. So let's create a function. So let's create a new file, and we're going to call this one name2.py. Okay, so what we will do in this one, we'll create some comments. So if I just start typing in there, this is a program that will get a name and add is cool to the end. So I've just typed in something I want to be a comment. So if I do that command and /, in Python, instead of it being / to do comments, it's hash. If we want to do many comments, you can do I think is it three things like this. I think that's also valid as a type of a bit like the / star / in C, but hash is the easy one for now. So we can just quickly type in some details like this. I usually put who wrote it and the date. So let's do the 26th today of July 2020. Right, and to define a function we use def, and we just define what we want the thing to be called. So what we will do in this one, let's call this coolify, and we put the little is that semicolon at the end of the line, and then when I press return, notice how it's tabbed in by about 4 spaces. Now in Python that's really important. The reason it doesn't need those curly braces like C does to define the beginning and the end of a block of code is because it uses indentation. And one of the reasons that they decided to do this is it actually makes your code more readable and more useful because it's more readable in that way. So what we will do on here is we will say we want to read in a value which is going to be name. So we will say let's do return name plus, and then let's say is cool, and that's it. We don't need to do any semicolons or anything at the end. We can just do that. So now to run that, we just do coolify. So if I want to do let's do my name equals, and then in fact let's do it this way. Let's do, what we want to do is we want to read in, so let's do input again. So my name equals input, similar to the last program. Please type in your name, and then what we'll say is my name equals coolify my name. What we want to do is convert that name, and then we want to print out whatever my name says. Okay, let's run that. So it's going to ask me for my name, and it says Kevin is cool. So let's have a quick look what's happened there. We've indented this code here. So this block of code is the entire function that's called coolify. And if we look in our outline, we can see there that coolify is the name of a function. We can see that it has a parameter which is called name, and that's what we actually return there, and we add to that name that's been passed to us is cool. My name is a variable that we've created just here. We treat it as a string, but really it's just an object. We don't really care what it is. And what we're saying is we want this thing that we've just created, see it says it's a string there, we want that to equal whatever's typed into the input. And then what we then want to do is say we want it to now equal whatever coolify does. So coolify is passed the name, it adds the name is cool to the name, and then passes it back to my name, and then we print out. So we created a function there, and it just executes the code top to bottom. So that's why it's looked at that, it's remembered that that's a function. It doesn't execute it right away, it waits for it to actually be called, which is it's called on that line there on line 10, and then it executes these 3 steps. So that's great if we are going to call this function directly. Now it is quite common practice to define a function that you call main. You can see it's even looking for us to type that in there. So if we do define underscore main, main is very similar to loop in Arduino. So anything that we put into main, remember we have to do the indentation. So I'm just pressing command and square bracket, the one that's right near the return key, and it's doing the indentation for me. And you can see it's got this little line here to indicate that it's indented. If I indent that a couple of times, you can see it tells me how many times I've done it. And I can use command and the other the left bracket to indent it. So indent or outdent, and then let's just do that one there. And then the last bit of code there is because it's not going to execute anything on here. Just need to put them brackets there. Sorry. So what we need to say is if is it main? Let me just do that define main thing because it tried to type it in for us. There we go. So if name equals main, then pass. What I want this to do, we can create functions as standalone libraries just by creating new files, or we can get them to run if this file is run on itself. And this is what's happening here. I'll take this out because I think that's probably confusing things for now. Right, so we've got a couple of things there. Now what happens if we want to store this coolify function and put that into a separate file just so that it's tidier? So I've got a question there from Svenborn. So what can you use instead of indenting when you have more nested stuff? You have to indent. That's the Python way. So you will find that if you're doing if statements, they might get quite nested, and the idea of that is that's intentional. It should work that way. I've got some example code I can show you, and we will do that as a bonus at the end of the video. We'll look at SMARS Lab, and you can see how some real world code actually works. So what I want to do is I want to create this coolify function in a separate file, because what I want to be able to do is include that in future things so that I'm reusing my code. If you remember from the top 10 tips that I gave, reusing code and creating libraries is a really important part of developing, because it means that we can spend time and effort making something work well, and then we can reuse that. So let's create a new file that we call coolify.py. It doesn't have to be the same name, this is just more of a convention, and I'm just going to copy that code there and put that into that file there. So let's just, this is the coolify code. And another convention that people use is, just after you've defined the name, it's good practice to tell the people that are going to be using this what this code does. Oops. So we put some comments there. So I'm going to do the 3 comments like that. Yep, that's worked. And this is a document descriptor, and there's tools that will look for these things after a function name, and the compiler, this VS Code, will actually look for these things. And when you hover over the name, it will look for this description and put it there as a sort of tooltip. So adds is cool to any string. Oops, passed to it. Okay, so that's all we're going to do in Coolify, and then back in our program. In fact, let's create a new file that we'll call name.3, and we're going to include this file. So let me just quickly check that on my code. So I'm just going to go over on my other machine. Just got sat here, and I'm just going to check to see that I've got this correct. So let me just pull up SMARS lab. So what we do to include files, like in Arduino we would do include and then the name of the library. So in Python what we do instead is we use import. So we say import coolify, like that. We don't need to do .py. It will assume that that's a .py, and it will assume that it's within either this folder or within the searchable path. So if you're not familiar with how terminals work, they have this idea of a path. The path is the hierarchy of folders, and the path is a special variable which is a list of all the folders to look through when you're executing a program. So if I type the word set, there will be path there. You can see these are the different things that it will search through when you're executing code. So that's why it doesn't need to know that it's the .py, and it will assume that it's in the same folder that we're executing. So if we do that, it means that we can use that function that is inside this coolify. So let's just do what we've done before. So we can say input name, and we will say sorry, I've done it wrong, name equals, and then we just type in what we wanted to say. Please type in your name. Okay, and then what we will then do is we will say name equals coolify dot coolify name. So you can see there we've had to type in the name of the library that we're using, and then the dot means within that we know that there is a function that's called coolify. Now to make that easier, because it might be that that's a really long thing that we have to type out, you can do import coolify as CL, for example, and you might shorten it to that, and that would mean instead of having to type in coolify as the library name, we can just do CL. And if we hover over that function now, let's have a see what happens. Can you see now where it says adds is cool to any string passed to it? That's because we did that little docustring right underneath the name of the function. So we're sort of documenting as we go, and we're making this really easy to understand, and for other people that are using this. Okay, so that's working well. Let's just run that and see if that works. So I'm going to type in a name, Kev, and we didn't print anything out, so let's just do print name. Let's try that again. So type in a name, Kev. Kev is cool. Perfect. So we've now created a library, which is Coolify. We can modify that, we can maintain that separate from our main program, and we've kind of separated the two interests there, and that's quite a good practice in coding. It means, in theory, separate people could be working on the Coolify library while we work on the main loop. Cool. So that's good. Let's save what we've done there. And now, if we look in our source code control, as well as the five programs that we've created there, there's all these other things that are in VMV/bin/ whatever. All these things we don't care about. We don't want to store them up in GitHub. What we want to do is tell it to ignore. We want Git to ignore this venv folder and this .vscode folder and this pycache folder. Python uses this __, the name of something __, as a way of saying this is a special reserved thing and you should treat it separately. And what's happened here is when Python executes, when it runs the code, it realizes it might need to use that function more than once. So rather than having to compile it every single time, it caches it. And this is what this pycache is. It's the bytecode. It's the compiled version of that file that we've just run. So we don't need that. We don't need to upload that. So what we do need to do is create a new file that's called .gitignore. And this is a special file that Git looks for, and anything that's listed in there, it will ignore. So if we do VS Code, we do pycache, like that, and we save that. We now go back to our source code thing, and you can see now these are the files that we do want to upload. These are the ones that we've changed. Everything else was irrelevant. So this gitignore file is a really good, useful way of keeping our code nice and clean and only uploading things that we're interested in. So what we can now do is we can synchronize this by committing. So before, when we were on the command line and we typed in git.add and then we typed in git-m and then a commit message, we can do this from within here. So within this source code control. So the message that we want to type in is added 3 programs. We can click on the little add there, and that will do the adding of all these things. So these are now all staged, ready to be committed. And if we press the little tick button there, oh, I've not saved all the files. Let me just save all. There we go. That's fine. It's just noticed that we've changed some files. Let's make sure we've had them in. And we click now the tick button. They're now locally cached, and we can see there's a little 1 sort of with an up arrow, and what it's saying there is this is a local change and we need to press this if we want it to synchronize to GitHub. So if I go now to GitHub and I just refresh this library, let's just bring this into view so you can see what's going on. I click on that. You can see there the branch called try KMC hello has been published less than a minute ago, but that hasn't changed the main branch. The master branch still has the original readme. The KMC hello branch is where we've created all our new code. So if we're happy with that, if we're happy that these things work well, and we need to create some tests to make sure that they do work okay, and we'll do that in a second, then we can compare and do what they call a pull request, and that will merge together the branch that we created with the master branch, and the master branch will then get all the files that we've just changed. So let's create a test just before we do that, because this is good practice. So we've created a function called Coolify. We need to write a little test for that. So let's call it test coolify.py, and what we will do is we will import unit test, which is a special unit, a special library for doing unit testing. And I think what we need to do there, let me just look on my code on the other screen to make sure I'm doing this correctly first time. So I just need to open up one of my test suites. There we go. And we just need to say class. So a class is a way of bundling together functions that we've used and variables that relate to those functions in a way that really sort of contains and makes into a sort of a component all the things that are related. So we typically have properties, which is the variables, and we have methods, which are the functions. And what we need to do on there, I'm just going to type it in just so you can see how this works. So we're going to call this test underscore coolify, and we need to say that this is of type unit test dot test case. And classes typically have an uppercase first letter. That's just the standard that people use. Okay, so let us now just make a little test. So what we're going to do is we're going to define a test that we want to run. So we want to check the name. So we're going to call this test name, and then we have to use something called self. Self in a class is it's referring to itself and any variables that it might have within it. So again, you can see the indentation there. It's indented it 2 levels now. And we're going to assert that something is true or false or equal. So let's try self.assert. And do we need to do assert? Let's try true. And what we'll do is we will say, just check in there. So what we'll do just before that, we will create something we'll call name, and we will call it Kev, and we will assert true name.coolify name.coolify. Right, equals, and then Kev is cool. Not sure I've got that right. So when we do equals, I think on Arduinos you just use a single equal to say you're assigning something a value or you're comparing values. In Python, to make it more specific, they differentiate between when you're assigning something and saying that is equal to that, or that should become that value, whereas equals is a comparative operator. So you say this is the same as that. So let me try that out. I'm not sure that's going to work, but what we'll do at the bottom there is we'll do that thing I was beginning to type before but then stopped, which is if main equals underscore sorry, not main, name. I'll explain what this is in a second. Then we want it to unit test dot main. Okay, so if we're going to run this file, this test coolify, we want it to look through this and we want it to compile all the different classes and functions within that, and then at the very end we want it to say if the name of this module is main, then unit test run that main piece of code. So the main piece of code is unit test.main, and that in effect will execute this code. So let's try running it and see what happens. So it's failed, and it's because I've done something wrong in here. Let me just quickly have a look at that. So I think what we need to do is we need to first of all import coolify. We didn't do that. As CL, let's do that, and then cl.coolify. There we go, that looks better. Let's try that. Perfect. So we passed a name in that's called Kev, and we've said we want to check if the coolify function, when it's passed the name Kev, it should return the value Kev is cool, which is correct. So we could say assert false and give it something else. So let's try self.assert false, cl.coolify name, and then equals just kev, that should be false. So if we run that again, it should, so there we go, it's failed one. Assert false, what have I done wrong there? I've not typed assert properly. Try that again. So that's passed because we've said it should be false. It shouldn't be kev, it should say kev is cool. So we've written some unit tests. We're happy that them unit tests test out our function properly. And now we can add them into our source code control. So added unit tests. We can add that to our staged area, we can commit that, and we can publish that. Right. So now we can merge this code together into GitHub, and then we can go onto the Raspberry Pi, we can set up virtual environment just like we've done already, and then we can get the thing working on there. And we will see why this setting up the virtual environment thing is really useful. I've got a really squeaky chair. Okay, let's have a look. Oh, is that the same, Sven? Sorry, I didn't realise that C is equals equals. I know some languages have just the single equals, but one of the reasons that Python is very specific, particularly with the indentation as well, is it's greppable. I don't know if you've used on Unix. There's a horrible command, a useful command, but it's got a horrible name called grep. And what grep does is it searches for things. So, for example, if I want to do PS, which lists all the different processes that are running on my machine, if I do AUX, let's just do I want to get more than just that, you see, PS, yeah. So if I've got a list of things, I want to search through all these different lines, and I want to find, has any of them got the name Z shell, for example, I can say grep. I then pass it something, and then I do a pipe command, and then I will say, I think I've done this the right way around. No, let's try running it, and then grepping it. And we want to find Z shell. I think that's how you do it. We try it the other way around. Grep Z shell. And pipe in ps-a. Is that the way around you do it? No, that's not the way you do it. It must be that way around. So we run that. We pipe in Z shell. Not found. So grep is away. I don't know why that's not worked. That should have worked. Let's get rid of that. The grep command is just a way of searching for things on lines of text. I've not got the syntax quite right there, but we can see what we're supposed to do. So we pass in some parameters, and then we pass in the string that we want to search through. So why am I showing you this? It's because Python is greppable. So the idea is that every line of code should be distinct and unique, and therefore make it very easy to find things. So sometimes in C and other languages you can have things that like the convention for having class names in uppercase, the first letter in uppercase, whereas instances are in lowercase. What that means is it's greppable. We can find these things much easier. You could do the same thing in other languages, but okay, let's get over to the virtual environment thing. So yeah, this is a good question. So we've saved our code, we've published that up to the branch on GitHub. And what I also want to do is I want to capture any libraries, such as a unit test, that I'm currently using. So if I do the word pip, this is the, in fact we can do it on the nice big window there. If I do pip and then freeze, what it will do is it will look and tell me these are all the current modules that you're using, the libraries that you're using, whether you realize it or not. So it, PyLint was something that was installed by VS Code, and these are some of the other ones that are being used in the background. Now I might not know what they are, but you can see there we've got the different version numbers of each of them. So the convention is you pipe them out to a file that's called requirements.txt. And that means that it's now got that list. If I just look into requirements.txt, we can see there it's exactly the same there. And you can use the pip command to say install -r requirements.txt, and it will go through and it will install in your area, in your environment, all those prerequisites. So this is a really important file that we need to make sure that we include. So let's just add in requirements.txt, and let's stage that, commit that, and publish that. And then over on GitHub, we can do pull and compare. So let's just refresh that, and let's do a compare and pull request. So it's going to say, I'm going to look through, it's able to merge the code because we've not really changed anything, there's no conflicts there, we haven't changed the same file in different areas twice. So because of that, I can just do a pull request. So I'm going to click on that. You can see there, these are the unique references, the hashes for each of these things that we've pulled in, and there's no conflicts with the base branch, so we can say go ahead and confirm the merge. It's also got details like my name, and there we go, that's it. So we can actually delete that branch now that we've finished with it. So just before I do that, I'm going to switch over on here back to my master branch, and I am going to go back to Git, and yes, we're going to say delete that branch. Okay, you can restore it later on if you think that that's a mistake. This is the beauty of source code control, you have total control over this. So if we go back to our master branch now, you can see we've got all the programs in, we've got our requirements.txt, which is just that list of dependencies that we needed. And now if we just do a synchronize, you can see it's going to pull down 4 changes there. And that's how quick it is to do it. And we've now got that branch that we worked on, that we tried stuff out, is now been merged back into the master branch. So now what I'm going to do, I'm going to connect to the Raspberry Pi, which is sat next to me on SMARS cam, that little Raspberry Pi that's just there. We're going to connect to that. So if I go SSH, I think it's Pi, and the name of it is the IP address 127. And I'll show you the bonus part of the video in a minute. We can have a look at SMARS Lab and what we can do with that using Python. This is where I want to get everybody to, so that you can help me out make this much better. We just need to bring everybody up to speed along with us. So once we've connected to this, it just takes it a second for it to wake up. It will connect in a second, and we can then clone that library that we've just created. We can create the virtual environment, and then we can use that requirements.txt to set up this virtual environment on this machine exactly the same as what we've just created on the Mac. And this is why this is a really useful way of working, because I'm working on 2 completely different platforms here. I'm working on a 64-bit Macintosh running is it Catalina, I think it is. Let's have a look what we've got on there. Yep, Catalina. And let me just go back to my main screen there. So let's go, yes, let's go to that one there. Yes, please make sure you like and subscribe as well. And if you comment, you may well be the comment winner for the next video. Again, that just helps me understand which videos are doing well, which ones have got topics that people are interested in, and which ones we should make more of. I could definitely see from the stats from the analytics that Python is something that people are interested in. Coding is something that people are interested in. Okay, let me just make sure I've got the right IP address there. So 127.127. And let me just make sure we're all good to go on that. Okay, let's just try that again. And what I'll do, I'll just unplug it back in. That's probably the best thing to do. There we go. So what I've got running on this Raspberry Pi, just while that's booting up, so that Raspberry Pi's got Python installed on it, and it has SMARS Lab, which is some software I wrote quite a while ago now. So if I load up that web page, so if we go to the play section and we look at SMARS Lab, you can see what this looks like. So we get a web interface. This is all using Python on the Raspberry Pi. We've got some controls there, so we press any of these buttons, we can get the robot to walk forward, sit down, stand up, turn left, turn right, clap and wiggle, and it'll keep a list of all the commands that we've run. And we'll see in a minute there's some new functionality that I'm adding in there. So things like Blockly, which I know they use on Auto DIY. That's for creating code designed for you know, kids really who are getting used to programming. They've not programmed before. It's a way of introducing very visually sort of building blocks together and blocking code. So Blockly is a Google initiative, and they've open sourced that, so you can use that to create your own code blocks. Right, let's give that a go now. Let's see if we can connect to, there we go. So I'm just going to type in my magic password, and there we go, there's our little SMARS. And what we can now do, if we go to, well, let's have a look. We go into our documents folder, and let's clone that Git repository. So I'm going to git clone, and then I'm going to type in the name of that repository that we uploaded to GitHub. And we called it lesson 8, and we called it Python. Is it Python intro? It might ask me to log in, it might just work without that. No, there we go, done. So now if I look, there's a lesson 8 folder, I go into that, I can now see there the files that we created. So let's do that step again where we do Python 3 -m venv. So that's going to create a new virtual environment on here. And it was not successful because something was not available. Let's try apt-get install Python 3 venv. It's a very helpful error message there. So I'm just going to install that. I haven't installed Python on here before, that's probably why it's just complaining about that, or that particular version of it. I think Python 2 is installed on here. There's some quite major differences between Python 2 and 3 when you're writing code. So for example, like the print statement on the original version 2, you didn't need to use the brackets, you could just use speech marks, and now they've made it into a proper function. You do. So just need it to do that. God, that's very slow. So while that's doing that, let's have a look at, while that's doing that, we can actually create a new window, connect to the same machine, and have a look around what we've got installed on there. So what I've also got connected up here, so if I just go to the split screen, let's go to SMARS cam actually, and if I just turn this round, you can see there all the servos are connected into the board there, and that's one of these boards, the PCA 9685 boards. It's actually that way up, and we've got the pins connected there to the Raspberry Pi header. These GPIOs are exactly the same type of technology as on the Arduino, so you have pins, GP, general purpose IO ports, that's what GPIO stands for. And I've also connected power, so I've got a power supply on my desk as well, just to give it some extra power to do the servos. So I'll just spin that back round again. I'll just put him there so we can see him. I've not got the rangefinder plugged in at the moment, but I have got all the servos wired up to the Raspberry Pi. Oh, good grief, that's going to take forever to do, isn't it? I'm going to cancel that actually. Let's see if it'll let me cancel that out. I'll be here all day doing that otherwise. Let's go back to this other window here. Let's just zoom in a little bit. And right, so I'm back onto here. What I'm going to do is I'm going to look into SMARS Lab. And we've got a virtual environment in there. Let me just move that up so you can see what I can see. So you can see here we've got this virtual environment. So if I do source venv bin/activate, I'm now in that particular virtual environment. I'm just curious to know what version of Python's in there. Yeah, it's got Python 3. And what we're going to do then is what we're going to do. The issue that I had there when I ran that command to create the virtual environment, there's another way of doing it using the virtual environment command. Let's see if we can use that instead. Just bear with me 1 second. Let's just see what we need to do there. And this is really the old way of doing it. The -m is the new way of doing it. So I'm sure it was something like virtual env. Yeah, so if we do like that, is that going to work? I need it to create a virtual environment using Python 3, that's the issue. And what it was saying, yeah, you see there it's doing a Python 2. But I'll let it do that, and then we will look back how when we bring in the requirements.txt and pip in a second. It might complain though because the Python 2's depreciated. They stopped developing that back in January, and there've been lots of warnings about that beforehand not to be using it. So you can see this is a lot slower as well to pull things in. This isn't just because it's a 0, this is because this way of building the virtual environments is a lot slower. So what it's doing there is it's basically copying all the binaries that make up Python into a folder, and all the libraries that are standard as part of that into this folder structure. So we've got a completely discrete version of Python there, and that means when we install the libraries, we're not over installing them to another instance of Python somewhere else, and it means that we can work on very specific versions of libraries, and that's quite important to us. It helps us separate out concerns. If you've got people working on different libraries, different versions, again, it just adds to the chaos of software development. So if you imagine teams of people are working on versions of Python, you get new members, join in maybe a year into development, and there might be a newer version of Python. They might be working on a slightly newer version of that library. So you really want everybody to be on the same versions, and using virtual environments is a way of doing that, making sure that that works. Right, so we've now got a virtual environment. We've got our venv. So if we do source vmv/bin/activate. I know this is going to be version 2, however, let's just try pip install -r requirements.txt. Let's see what it says. So it's going to go off to pip. It's going to grab the, see there it says about depreciated in January. It's going to look on PyPy, and it's going to look to see can it find these requirements. And the reason it's giving this error message is we've used Python 3 libraries and we're trying to install it in a Python 2, but that's how we would do that. What I might do is get it to try that command again to install, but I'll not keep you waiting. I'll just see if it does what we need it to do. Let's see if it'll do that in the background. It might be quicker. Okay, so while it's doing that, yeah, it's 38%, 40%. We might be able to get it to do it properly. So while it's doing that, I'm going to run in this virtual environment, which is on 3.5.3. I'm going to run SMARS Lab, and we're going to connect to it over a web browser, and we're going to control this robot. So we do Python SMARS Lab. And we'll have a look at some of the code. Hi Chris, how you doing? Nice to see you on here. Great stuff. Right, so SMARS Lab is now running. It's using this framework called Flask. Flask is a web server. It makes it very easy to create websites and host them. So now if I go to my web browser, I go to the browser, sorry, the IP address of the Raspberry Pi, and it's on port 5000, and I connect to it. We will see in a second might just be a little bit slow because this is installing on the background, and these Raspberry Pis are not particularly powerful. The Zero is, I think it's only got a single core and half a gig of RAM, I think it might be. Okay, just bear with me while it does that. Yeah, it'll be slowing down because of that. What we can do to check, we can use the word top, but we've not got a free terminal to do that with, so I'll just let it continue doing what it's doing. It has very nearly finished doing that install there, and momentarily we will see SMARS Lab spring to life. Poor thing, I'm going to stop it again. That's just too much for it. Yeah, there's a top command if you've ever used Unix before, and what that will show you is like the top processes that are running. Has it actually just shut down that? I think it has. Yeah. So there's a slash shutdown command that I've built into SMARS Lab so that I can stop the server from running. We look at this now and just refresh it. We should get the there we go. We should get the thing running. So let's make this a bit bigger. So this is SMARS Lab. So if I press these buttons, the robot will spring to life. So let's go onto the split screen. Let's go to SMARS Cam. I can't really do the split screen unfortunately because we can't see the code at the same time. But what I'm going to do, I'll flick between this screen where we can issue commands such as sit down, and I will then go to the SMARS Cam, and we can see what the results of that are. So let's get that open there. Let's start issuing some commands. So let's go backwards and forwards, left and right. Okay. Still seems to be a little bit laggy. I'm not sure what's going on there. So I can see on the Raspberry Pi, if I look onto the host screen there, I can see that I've issued some commands to it, such as up and down. That's because when I've clicked those buttons, and you can see in the command history as well, we can see the telemetry. That's all the different angles that each of the different servos are at. So the front left leg, which is, if I go to SMARS Cam, front left leg is this one here. That's the front right leg, back right leg, back left leg. The foot is the very end part of the limb. And let's just issue that command there. Not sure why that's being so slow. Let's just give that a refresh. And let's just stop that. Sometimes I find that the Raspberry Pi seems to glitch out if things are not running quite the way they should do. That's why. When I pulled up the robot, it disconnected from the external power, and if it tries to run those servos, I'll just wire that in actually. If you try and run the servos just from the power that's coming from the 5 volts from the Raspberry Pi, it just overpowers it, so it'll just rebooted. That's what's just happened. So that's a bit frustrating that. Let's just try and screw those in tight. Not sure. I'm not convinced that they're actually powered in there, but I'll hold them in. What I'll do is I'll just reconnect on another terminal to that machine, and we're nearly done. I just want to show you this actually working so that we can see what we can do with Python and robotics. No, I think that's just disconnected. What I'll do for next time, I'll get this up and running. I want to show you the code and how this is actually working. So I'm aware that we're about 20 minutes over our lesson there. Okay, what we'll do is we'll go to GitHub. We will look at the SMARS library, and SMARS lab, and we'll look through some of the code there to see what's going on. So smarslab.py, you can see I'm using Flask. Let me go to the host screen. There we go. There I am. So you can see on here we're using Flask. We're using something called MarkSafe. We can ignore that. Flask Bootstrap is the web framework for building websites very quickly and consistently. And there is a module that's called SMARS Library, and that's one I've written and I published to pip to make it more reusable. So I've created an entire library of SMARS robot stuff. So I've created a robot there called SMARS, created an app on the Flask, and this driver thing is to do with testing. So obviously when we try and test code up in GitHub, it doesn't have this PCA 9685 board, so we have to have a way of telling it if it can't detect one of them to do something else, and that's what this driver. So if I say do not use this, it can detect that. So if that's true, if it can't detect that, then it can say there's an error message, and it can skip over certain commands in our code. And then these app.root things are to do with Flask and how it captures when you're hosting a website and you want it to do like /about or / all the different parts of the URL there. You can get it to respond back. So there's a control API, and depending what we post to this control API, we can do up, down, left, right, all the different commands that we've got there on our interface. Each of them buttons essentially just posts to this API, and because we're capturing that, we can also say the command history equals whatever the last command was, and we post that to the web page as JSON, which is a way of storing data and passing it around. It's JavaScript object notation. That's what JSON stands for, and it's just a way of curly bracketing and speech marking, comma separating blocks of data. So it's kind of human readable as well as being machine readable. And yeah, that's how it actually executes the code. So each one of these things, smars.wiggle, smars.sit, they're functions within the library, within SMARS library. So if we jump back to our repositories and we quickly look at SMARS library, we can see how it does that. So there's SMARS library. So we go to SMARS library itself, we go to the main code, and we can see that it imports the Adafruit PCA 9685 board, imports something that I've called channel, which is just about the different channels that are on. I'll model that as a separate class. We say let's try and initialize it. If we get an error message, we can say that it's not found the driver, which is fine, and if it can't find the driver, it sets that do not use to true, and we can then use a different code path later on in our tests. We do things like setting the minimum and maximum values for each of the servos, the sleep count, which is similar to what we did when we were doing the movement later in earlier videos, and we've got some error checking on there as well. So let's have a look there. We modeled the leg, so each of the legs is actually a separate instance of a class called leg, and they've got things like minimum values, maximum values, and that's because each of the limbs has a different range of motion. It doesn't all go from 0 to 180 degrees, some go from like 36 to whatever. So that's what that's about. We've got those three different positions: swing, body and stretch, and whatever the current angle is. So the swing angle is if it's at 45 degrees, the robot's got its limbs at 45 degrees. Body is when they are sort of pointing like that towards the body. Stretch is when they're sort of forward, it's sort of stretching out like that. And whatever the current angle is, that's captured there. And then invert is because we can use the same code, but when the servos are flipped over and oriented in the opposite direction because on the other side of the body, that's what we can use there, to just use the same code but just invert it. And then we just initialize the code. We set some defaults up. When we say set body, we can say what we mean by that. We can just set the angle. We can look if it's inverted or not, and we just do the opposites for them, min or max. So you can have a look through this code yourself. I'll put some links into the description. You can see on GitHub, it's just my username /SMARS_library, and just hear the robot there, the servos are struggling to keep up. And yeah, you can have a read through, but we can use Python and we can develop much more interesting things than we could possibly do on an Arduino, such as things like OpenCV, which is a computer vision library, so we can get it to object detect, and we can have little rectangles over things where it's detected a face, and it can follow faces and follow people around. We can do that, so that's reasonably trivial, believe it or not, and that's something that we'll be looking to implement in later sessions. So there's a question there from Svenborn about so is it normal way to communicate with the Raspberry Pi, or just more optimal for more systems? So I would say Raspberry Pi just gives you more options. You don't need to necessarily use Python. You could use a different language. You could still use C, but because you've got a full Unix computer running on board, you can do way more than you could with an 8-bit chip. So these Arduino chips, they're actually quite expensive as well if you think about it. That's, if you buy an official Arduino board, they're about 30 pounds, whereas a Raspberry Pi Zero, these are about £5. The actual memory card costs more than the board itself, and this is one I've got with a motor shield, so this is a Motor Zero, and it's got things at the end there, so we could actually have this sat in the SMARS instead of the Arduino. It's a smaller footprint as well. It does use a bit more power, but we can address that. We've got a bit more space to put more batteries and things like that, and we've got built-in Wi-Fi and built-in Bluetooth as well, so we don't need to have extra chips for that. So I would say it's more than just optimal. It's there's just more features. It's richer. We can do more with it. We've got more memory. So instead of just having 32 kilobytes of RAM on the Arduino, we've got half a gig of RAM on the Raspberry Pi, as well as much space on the memory card, 64 gig or whatever you want to have, tons of space. So that's why I think it's quite cool to be able to use Raspberry Pis for this, and to learn Python is quite straightforward. So I hope you found that useful today. The next sessions that we're going to be doing on Tuesday will sort of enhance this. I'll do a bit more prep. We'll get this thing walking, and we can walk through this code to understand how to develop robots further. So yeah, please comment in the video on YouTube. Whoever's got the best comment will get mentioned in the next video, and I will see you all on Tuesday. Please like and subscribe, and I'll see you soon. Thanks everybody.